and I'd like to thank, of course, the organizer for the invitation, and I would like to present some remarks on this that I call ballistic aggregation. I don't know really too well how to call it, but let me. So this is joint work with Stéphane Michler, who is in Paris at Dauphine. So I'd like to. Perhaps the most interesting part is the motivation and the introduction, and then I will try to describe results in the general case, which is very easy. There are very, very short results, and then to simplify more and more until the even simpler case, which is what I call the constant case. So let me remember how you can describe what I call ballistic aggregation. There are several definitions. I found that one rather clear. It was given by these people in paper 19. So you consider a set of particles of a given radius which are moving. So you start with an initial velocity and you are in a space dimension of dimension d. So the particles are moving along following their velocity, and then when they collide, they form a larger particle. You add the masses, so it's a coagulation, it's an aggregation of the particles. The radius is assumed to grow so as the volume of the particle is proportional to its mass, and the velocity of the new particle is determined in order to have conservation of the momentum. Okay, so the particles are moving freely between the collisions. They collide. They aggregate, they form a particle of mass m plus f prime, m plus m prime, and the velocity is such that the total momentum of the collision is preserved. Okay? And well, that's a simplified version of phenomena which appear in several contexts. I will give some examples in the conference. So some remark. Just to start with, so the particles and clusters. After the first step, you have clusters of particles behave as free particles between collisions. So you have free behavior of the particles. There is another scenario for this kind of coagulation phenomena, which is scenario where the particles move according to Brownian motion. When they collide, you add the two masses again, and the particles, you don't care about velocity. The particles have not a particular velocity, they just move by Brownian motion. And that case is the case which has been much more studied in the literature. I will probably mention some results in the following of the talk. But nevertheless, the ballistic aggregation seems to be necessary in some applications. So it's clear that in several applications, in particular in aerosols or in sprays, for example, in combustion, or in the evolution of what people call planetesimals in astrophysics, the real phenomena seems to be rather ballistic aggregation. So after a while, the problem has a very nice geometrical aspect that I will neglect completely, but just to start with, let me show you some pictures. So the geometry of this kind of ballistic processes of the clusters that you obtain with this ballistic is very different, or rather different, from the geometry you obtain with particles moving by Brownian motion. And I've tried to find in internet some pictures. So that's a picture of what people call particle cluster diffusion limited aggregation. So you put a particle in the middle, then you put a particle in that corner moving by Brownian motion, and as soon as the second particle collides with the first one, you stop the movement, you put a particle, you get your particle stick there, and then you put another one, and after several thousands of particles you get a tree like that. So that's when the particles are moving just by Brownian motion. If you do the same thing with ballistic aggregation, you get something which is not too different, but which is different. So not very, very different, but it's definitely different. And then you can do the same thing if the clusters are moving, so not just a particle clustering or aggregating to a cluster, but clusters moving and colliding, and you get, so the color has nothing to do with the diffusion, it's just, so that's cluster-cluster aggregation when clusters are moving by Brownian motion. Okay, that's the kind of geometry, and that one is it's not very clear, that picture is not the best one, but that one is when the clusters are moving by ballistic aggregation. So the geometry definitely is different. Okay? Now, what is the what people are interested in mainly? For example, this Carnevale et al. Who described the ballistic aggregation, as I said at the beginning, are interested in the evolution of, for example, the density of particles. Okay, and they give a very general scaling argument in order to give a power law for the behavior of that density of particles. The argument is very rough. It's essentially a dimensional argument. I don't think I will give it in detail. They start assuming that the density of particle is going to decrease following that law, where tau is a mean time between collisions. It's not very hard to get convinced that the mean velocity of the particles, the mean radius of the particle, and the time tau, which is here, are related in that way. And then you get a slightly more detailed balance equation, which is that one, where you just have n and that mean square velocity v here. Okay, so that's very general, and here you don't have made essentially any assumption. Now the main problem of the argument comes here. There is an assumption about the fact that the velocities of the particles are uncorrelated. So if you assume that the velocities are uncorrelated, the momentum of a particle of, say, mass m is given by the sum of the momenta of, say, m particles of mass 1. And so the momentum of the particle m scales like the mean of the momenta of m particles of momenta 1. So p scales like square root of m. And then the velocity, which is p over m, scales like m to minus 1 over 2, which is the same scales like n to the 1 half. So you plug that in the equation which we had before, and you get here that power law. So that's one of the results by Carnevale and Pomo et al. So the density of particle scale decreases with time like 2d, d is the space dimension, over t plus 2. Okay? So from now on, let me call small m the mass of a particle, p the momentum of the particle, and v the velocity of the particle, okay, at time t. Now, what are the previous results that we have found in the literature about the problem? So we haven't found too many. It's not very easy, at least for us, it wasn't very easy to relate between them, to understand which were the relations between them. So I tried to present them in a coherent way, but so let's try. The first one I would like to quote is that work by Zhang and François Lévraz in '93. So they use the arguments by Carnevale et al., where they suppose that the velocity of the particles scales like minus 1/2 of the mass. And then they use the classical Smoluchowski coagulation equation. They say, okay, the particles are colliding. It's a coagulation process. If the velocity of the particles is like m to the minus 1 over 2, it's reasonable, I will come again on that, but it's reasonable to take a kernel, a coagulation kernel, which is of that form. So that comes from the geometry of the particles. D is the spatial dimension, and that comes from the difference of the velocities, that minus 1 over 2, which is here. So they end up with a classical coagulation Smoluchowski equation in the discrete case with a collision kernel which has a homogeneity which is lambda 1 over 2 minus 1 over d. Now it is known that, at least formally, how the function f behaves for large t's when f is a solution of that coagulation equation. And that's what Zhang and Levras do. So the standard theory of classical leads formally in the sense that we are not able to prove that the solutions of the coagulation equations actually behave like that. So it's very reasonable, but for that kind of kernel of coagulation, we are not able to prove that. But formally, what you can see is that n of t, which is the density of particles, which can also be expressed as the total number, essentially, as the total number of particles, scales like t to the minus 2 over 2d over 2 plus d. So that's exactly the same power law as for Carnevale at all. But, so that's the good news for, but the bad news are the following. If you still use the standard theory for the coagulation equation for that homogeneity of kernel, the predictions on the values of f of t and j for g fixed and t going to infinity, the prediction of the theory is completely different from what you can see in the numerical simulations that they perform. Even in 1D, for example, for g equal to 1, the theory predicts exponential decay. And the numerics says that the monomers decay like 1 over t. That's the prediction given by the numerics. So there's a very, very strong divergence between the prediction of the coagulation classical Smoluchowski equation and the numerics done on the ballistic aggregation. Of course, the problem can come from is there any relation between Smoluchowski equation and the ballistic aggregation phenomena? So that's part of the discussion, and these two papers by Jean Bertoin show that there is a relation, a deep relation between the ballistic aggregation for particles and Smoluchowski equations from a probabilistic point of view, but the relation is very clear. So perhaps it's not as simple as that one, but there is a relation. So that's one of the results I wanted to. The second result, which is quite different in every sense, is by these three authors in 2000. So they solve explicitly the ballistic aggregation problem, as they say, in closed analytical form. So they give an explicit solution of that in 1D, but with very particular initial data. So the initial data are built in the following way. So you start from a discrete problem. So you put discrete particles of mass, of fixed mass f naught, located on sides of any lattice at distance delta. Okay, and you distribute the momentum of the particles in that way, where beta is a fixed constant. And then you take the limit. So you take the limit, delta goes to 0, m naught goes to 0, but the density of particles is constant. So it's a kind of dust. You build a kind of dust, initially a kind of dust, which is uniformly distributed in R. And the momentum, since m naught is going to 0, you're going to concentrate like a Dirac at the origin. Okay? So it's a very, very particular kind of initial data. Now, what the authors show is that with that initial data, they can transform the problem in an equivalent problem. They call it a Brownian motion problem related with hydrodynamic formulation of ballistic aggregation. So that, I will come back on that in a minute, I think has something or a lot to do with the conference the very nice talk by Jan. I think I'm not able really to explain the relation, but I think something should be said about it. So that's the second result. So what do the authors obtain? Well, they obtain an explicit solution of that form, where sigma depends on the initial data, is the second momentum of the initial data. Phi is an explicit function. They have expressions for these functions I and j. The important thing for me, or for what I would like to do, is the scaling form of the solution. Okay, the solution has a very precise scaling, m over t to 2/3, t 1/3, p over m, t to the minus 1. So, in particular, where in 1D, the density of particles decreases like -2/3, which is exactly the power predicted by Carnevale et al. For d equal to 1. Okay? Something strange about that solution is that when you fix t, say, and you let the mass go to infinity, the behavior of the total mass is rather strange. It behaves like it is extremely fast at infinity, and Levras suggests that then can be due to the very special initial data which is considered by the others. Okay, but that's an explicit solution, an exact solution of the problem. Now, third, a reference by Trizak and Krapivsky in 2003. So they show, of course, the problem comes from that assumption of non-correlation of the velocity. So they show numerically again that while the numerics performed by the authors suggest again that this is not true. That is not always true, and they do the numerics with a kernel which is v minus v prime, which is p over m minus p prime over m prime. Okay. Well, they consider a case where a constant kernel, a constant coagulation kernel, for which the behavior is this scaling is correct, and then they obtain the power law predicted by Carnevale, but just for that constant kernel, which is and it's very easy to find a lot of references where people use that assumption. They assume that there's no correlation in the velocities of the particles, and then they simplify the model to a Smoluchowski, a classical Smoluchowski coagulation equation with the kernel of the form given by Levras and Jan. Okay. So what would we like to? Of course, we would like to solve the problem, but we are not able to solve the problem. So what have we done? We'd like to understand these different results. We have some scalings, we have some numerics, we have some explicit solutions. There's no way to relate them. Is there? They don't quote them. To get some rigorous estimates, even in the simplest case, is there a way to obtain rigorous results, to know if that is true, if that is not true? What are the scalings of the solutions between v, m, p, and time? So possible scalings, and say something, if it's possible, about self-similar solutions. Okay, so these are now. It's not clear for me how do you so the ballistic aggregation problem has at least two formulations, two precise formulations. One which is given in the form of kinetic equation that I'm going to describe right now, and the second one which is given in terms of hydrodynamic equations, say, or that I'm going to write down in a minute. So we will consider that formulation here. So that's what I'm going to describe precisely now. So let me consider f, the density of our particles, which depend on time, on space, mass, and momentum. Okay? These particles move along with their velocity, p over m. and they collide from time to time. They collide, and that's described by that kernel here, that integral kernel, which is a, say, almost a classical coagulation Smoluchowski kernel, but depending on the velocity. So these two terms are the classical terms. If you drop the p dependence, you get the coagulation, the Smoluchowski, the classical Smoluchowski equation. Now we're integrating in all the momentum variables just to obtain a kind of balance equation for all the particles. Okay, so that's the formulation I'm going to use in order to describe this set of particles which move freely when there is no collision, and when there is a collision, the particles aggregate. So here's the description of the aggregation. I'm just describing it in the next slide. Okay, so the microscopic, what happens at the microscopic level when two particles collide is encoded here. I'm going to describe right now. Now, the particle py, so y represents the variable m and p. So that's a particle with mass m and momentum p. That's a particle with mass m prime and momentum p prime. They collide and form another particle with mass m second and momentum p second. And the conditions are that you preserve the mass, you preserve the momentum. Okay? So in such a way that I'm going back to the equation, that equation, at least formally, preserves the total momentum and the total mass. Of course, that kind of equation was already known for a long time. For example, in combustion, in sprays, in combustion in gases, you can find a very, very similar equation in the book by Williams in 58. In astrophysics, you can find things probably even before. I'm not sure, but so that equation, a kind of Smoluchowski equation involving the velocity, was already known. No? Okay. The kernel K. So the kernel in general, you can find a lot of different kernels, but in general, the structure is that one. You have a function here dependent on m and m prime, where I included the sticky probability, so the probability that the two particles meet, and the collision cross-section, which depends, say, on the geometry of the particle, and then b of v and v prime, which depends on the relative velocity of the particles in general. Okay? So these are two. That's perhaps the most usual example in 3D. So that's I've taken the sticky probability to be 1. So that's what I call the collision cross-section, and that's the difference of velocities of the two particles. But you can also find something more different. For example, in the context of stellar dynamics, by these authors. And probably you can find different powers here. So HS means for hard spheres, because here you have a power 1, and NP comes from Newtonian potential, because that comes from a modification of the classical Newton potential. Okay. Now, an important remark is that the collisions do not conserve the energy. You dissipate energy. It's a very simple calculation. The difference of the energy of the outcoming particle and the sum of the energies of the incoming particles is strictly negative. Okay, so that's the kinetic formulation that we're going to. But okay, so I remember here an existence result just to get rid of it. So you can prove that equation under some conditions on the kernel, which are here. I don't. Probably you can do better, but and if the initial data is good enough, then you have the initial data is non-negative, of course. Then you have a solution which is global in time. It's a classical solution, and that result applies for the two examples I've given here. Okay, so I thought I couldn't speak about that without making a reference to that formula. So that's the other formulation of the ballistic aggregation. So you consider the mass density of the particles and the velocity of the particles, and you describe the particles which are just moving following their velocities, and you have conservation of the momentum and transport of the particle density. So that's sometimes called the pressureless gas, the sticky particle system. I don't know very well. I don't know if Zaldovich was the guy who introduced it. I don't know exactly the precise relation. I wanted to ask to Jan of that with the model U. And here I've quoted several references. Probably they are not complete, but so is there a relation between that system and the kinetic equation I wrote before? As usual, at this formula you can do something, which is suppose that F is very classical. You suppose that F starts the kinetic equation, then you look at the evolution of the momentum of the function F, and you get a system of that form for two functions, phi and a family of psi k. I wrote them in that way. So that's not exactly the system yet, but well, if you have a kernel, a reasonable kernel, in such a way that these guys are steady states of the system. Okay, so you need a kernel allowing for steady states of that form, which are a bounded measure in M, and a Dirac measure for the velocity, where u is a given vector. So if these are steady states, and if that is a solution of the kinetic equation, which is an equilibrium for any t, for every t and x, so if that solution has that structure here, then you can show that this rho f and uk satisfy the pressureless gas system. Okay, so these are solutions of that system here. Okay, so it's, of course, it's not a proof. It's just so there is a relation. Probably a lot of work has to be done to understand it better, but so I will not consider that system. I will just consider the kinetic formulation. Okay? So I come back. I've tried to find another name for the equation. I didn't find it, so I still call it Smoluchowski equation. And when I will refer to the classical coagulation Smoluchowski, I will call it classical coagulation Smoluchowski. So I'm going to look at the kinetic equation. I drop the x dependence, so I consider that the set of particles is homogeneous in space. Okay. So no x variable, so the transport term drops, and that's really very, very similar to the Smoluchowski equation. The kernel depends on m, p, m prime, p prime, and the function f, of course, depends on t and on p. Now, for that simplified problem, you can also obtain an existence result, which I quote here. You have, under slightly stronger assumptions on the kernel should be k and not a. And if the initial data is symmetric on p, then you can obtain a global solution. Okay. So this was proved by Nicolas Fournier and Stéphane Michler some years ago. But in that case, that only applies to that example. But we'll see that that's not a problem, because we're going to restrict ourselves very much on the kernel. So this problem has global solutions which are unique in the set of solutions which are very good. And they obtain some, well, it's a product, it's a byproduct of the existence result. They prove that some moments of the solution tends to zero. So we're going to obtain, say, qualitative properties of the solution. So these moments with alpha and beta in that set, I made a picture here. So that's alpha and that's beta. So for the alpha and beta in that set here, there's no limitation. Okay, the momentum is going to 0, but there's no rate of decay. So these are only very indirect estimates just by compactness. So there is no estimate in general for the decay rate of this moment. So our first result and unique result in the general case is that at that point there you can get a rate of decay. So if you have a rate of decay for that, and you know that in all the other points you tend to 0, just by interpolation you can obtain rates of decay, which will not be optimal, of course. Okay, so let me skip that. Well, just skip that result, but that's the only point for which you are able to obtain a rate of decay of the momentum of the solution in the general case, which is, well, so you suppose that the kernel has a very, very particular form. Suppose the initial data is good. Suppose that the initial data has a momentum of that order, so -1/3 in m, 1 in p. Then that moment tends to 0, and you tend to 0 like 1/t. Okay, that's an extremely partial, but that's the only thing where, because the geometry, the fact that the kernel really depends on m and p makes things much worse than in the coagulation case. Really, it's amazingly worse. So let me so let me give you the result. So we started to simplify the kernel. Are we able to say something when the kernel only depends on the momentum? So that's not necessarily very physical. I haven't seen any physical example where the kernel only depends on the momentum. But let's see if we can say something clear and precise when the kernel only depends on the momentum. So if the kernel only depends on the momentum, the equation, of course, simplifies in the sense that you can integrate the equation with respect to m. If you integrate the equation with respect to m, you obtain an equation which is a kind of convolution equation. And in that case, you can obtain much more precise estimates on the momentum. For example, if the kernel is like p minus p prime to the power gamma, then the moment of order gamma of the solution decays exactly like 1/t. If the kernel is like p minus p prime and you are in one dimension, then you can obtain estimates for different moments. And some of them are, so m1 is like 1/t, that's normal because we're in the case gamma equal to 1. But for instance, that one will allow us to say something about the general argument by Carnevale et al. Let me go to that. So we can repeat the argument, the very general scaling argument, if you take the kernel p minus p prime. It's not very difficult. That was done by Trzak and Krapivsky. The argument gives in that case that the density of the particle should go like t to the minus 2 in any dimension. So Trzak and Krapivsky did some numerics, and the numerics do not confirm that behavior. The estimates, the estimates that we obtain here say that you cannot behave like that in dimension 1. Okay, the result is only valid in dimension 1. In dimension 1, this result is false. So definitely, this argument doesn't work. That's clear, in general. You can also deduce something about the self-similar solutions. It's not too much, but you can say the following. If you start with what I call the Small-Shopsky equation, you can try to you look at the scalings, and it's not difficult to guess that you could have a self-similar solution of that form for some powers which must be related like that. Now, if the kernel only depends on p minus p prime to the gamma, that would give you a self-similar solution for the reduced equation that you have obtained when integrating with respect to n. And for that solution, you know exactly the decay of the moments. And you observe that the result that you obtain in the estimates of the moments are incompatible with the decay of the momentum given by the self-similar shape of the solution. Whenever the profile of the solution has a sixth moment with respect to the momentum. So what you deduce is that you cannot expect a self-similar solution for the original Smoluchowski equation, for which the profile, what I call here theta, has a momentum over the 6 finite. So either you have a singularity somewhere, either you have a heavy tail. Okay? You can also consider the case where the kernel only depends on the masses. So it does not depend on the momentum, just on the masses. So that's something sometimes called Maxwell models, because that approximation was done in the Boltzmann equation by Boltzmann, and corresponds, for example, to a potential of that to that power for the potential. Now, what we obtain in that case is the following. You can obtain a whole family of solutions in the following way. So take a function a which is homogeneous of order 1 over theta for any number of theta positive, and take the Fourier inverse of that function, the exponential of minus a, and suppose that's non-negative, just because we want non-negative solutions. And let f, capital F, be a solution of the classical coagulation equation. So in that case, this function, where d is the dimension and theta is that number here, that is a particular solution of the Smoluchowski equation, depending on the momentum of the, depending only on the kernel only depends on the mass, but the equation depends on the momentum. So that gives you a particular family of solutions of the complete equation. In particular, theta in principle is arbitrary up to that constant, up to that condition here. So that gives you a lot of solutions with different scalings in P over M. Okay? So for example, if you want a solution, while a Fourier inverse to be non-negative, you need the function to be what is called positive definite. An example of these functions are A of that form. Okay? Now, if you take any power theta greater than or equal to 1 over 2 and any function A of that form, then you will obtain a solution of the Smoluchowski equation. So you can obtain solutions scaling like P over m to the theta for any value of theta bigger than or equal to 1 over 2. Since you are able to find self-similar solutions f of the coagulation equation, joining the two results, you can obtain self-similar solutions of that form or of that form for the complete Smoluchowski equation with very different scalings in P and M. Okay? So I think I'm out of time, so I think I'll stop here, and I thank you very much.
Are questions or remarks? So we thank the speaker again.